Hello, and welcome to Lecture 8 on Chapter 8 from Astronomy Today. The topic is the Moon and Mercury. We're going to be talking about these two worlds, one being a planet, the other being Earth's moon, because they share some commonality in terms of their surface features, in terms of being mostly dead, in the sense of not having active cores. They're small, they don't have much atmospheres. They do have some key differences as well. Okay, so let's get into it. Okay, so we're going to talk about orbital properties, then we'll talk about physical properties. Okay, kind of applying to both. Then we're going to talk about specifically the surface features on the Moon and Mercury. We'll then talk about rotation rates, because there's actually some real interesting things about rotation that Mercury and the Moon share, but there's some key differences as well. Then the idea of why air sticks around and also why it doesn't. So that's maybe why we don't see atmospheres on either Mercury nor the Moon. We'll talk a little bit about lunar exploration, the things that we've explored on the Moon. We'll talk about lunar cratering, right? Because you can obviously see lots of craters on the Moon, and the surface composition. Then we'll talk about the surface of Mercury, also covered in craters, but there are also some key cliffs that Mercury has, which you don't see on the Moon. We'll talk about the interiors of the world. I said that the interiors are mostly dead, and that's true, but there is something interesting going on with Mercury's interior, certainly. And we'll also talk about the origins of the Moon. Where do we think it came from? All right. And then a little bit about the evolutionary history of the Moon and Mercury. Okay, well, let's get into it. Okay, so distance between the Earth and the Moon has been measured to accuracy of a few centimeters using lasers. Okay, so we obviously have a good idea of the dynamics of the Moon. We can use Newton's synthesis of Kepler's third law to get an idea of how far that distance should be from Earth to the Moon. But most accurately, we can actually bounce a laser off the Moon. Okay, now that's wonderful, and it gives us very accurate data. As far as Mercury, Mercury is interesting. We also know the distance fairly well, but one thing we know about Mercury is that it's actually difficult to see at night, quite the opposite from the Moon, which you can clearly see go through phases. It's very prominent when there's a full moon, which rises when the sun sets. Mercury basically is only visible right at sunrise or right at sunset, okay? Because it's never far from the sun. Because if we think about our line of sight from Earth, then we see that Mercury's orbit, shown here, is literally close to the sun. There's no way for us to view Mercury, say, in the middle of the night, because the middle of the night for us is looking away from the sun. Well, if we're looking away from the sun, Mercury's not over there, because of course Mercury is between us and the sun, and furthermore, it's rather close to the sun. Okay, now that's the same case for Venus, right? Also, Venus tends to be close to the sun, but you might see it an hour after sunset, whereas Mercury really could only catch it a few minutes after sunset or right before sunrise. Okay, so Mercury goes through phases, okay? And we can see those best at maximum elongation, okay? That's the relative positions of Earth and Mercury to the sun. And we can see Mercury go through phases of being new, because essentially all the reflected sunlight from the sun is hidden from us, so we're just seeing the silhouette of Mercury. We can see half phases, gibbous as it starts to grow, all the way to a full Mercury when Mercury is on the far side of the sun from us. Okay, so we can absolutely see those different phases of Mercury, which is also true for Venus again, because both Venus and Mercury are between us and the sun. Okay, so we see those planets go through phases. We don't see the other planets go through those same phases because they're never going to be between us and the sun. Okay, like for example Mars. Okay, so let's look at some of the details, the physical properties. Okay, so we've got Earth, right, about 6,380 kilometers, right? So that's the terrestrial planet of Earth. We can see that both the Moon and Mercury are much smaller, both of them under a third of the size of Earth. The Moon smaller than Mercury. We can compare their masses. Okay, we see that Mercury is significantly more massive than the Moon, not quite 10 times more massive, by looking at the order of 10, the order of magnitude, but close to 10 times more massive. It is denser than the moon. It has a much denser core, okay? The moon is not made of very dense material. And we see that indeed here with the rather dramatic difference between the densities, okay? So we see that Mercury is significantly denser than the moon. Now, is Mercury a super dense planet? No, just compare it to the Earth. It's actually slightly less dense than the Earth, and that's because the Earth was just through whatever processes able to accumulate some rather dense material, and and so we have a large core of metal material. The real striking number here is the moon is so low density, and we're going to come back to that briefly when we talk about the origin story of the moon, the best theory about where we think the moon came from. This last number here, the escape speed, has to do with the actual gravitational pull. So this is how fast you'd have to be going to shoot a rocket, or how fast a rocket would have to be going in order to escape the gravitational pull of that world. So here we see for Earth, the escape speed is about 11,000 meters per second, or 11 kilometers per second. That's how fast we have to shoot rockets in order to get them away from Earth, okay? To send them off on interplanetary missions. The escape speed is much less for the moon, right? It's less than half of that. So it doesn't cost as much fuel to get off the moon. And Mercury is somewhere in the middle. Okay. All right, so surface features of the moon and Mercury. Well, the moon has large, dark, flat areas due to lava flows, right? So you see these when you look at the moon. They're called the maria, okay? The maria. Early observers thought they were oceans because they do look dark, right? We know that water has that property of not reflecting light, whereas obviously, the dusty plains of the moon, the dust that is between all the craters in the moon is very reflective. So it certainly stood to reason that early observers thought that perhaps those actually were oceans on the moon, but they're not. It's just darker rock that is the maria. So it's dried lava flows, big expanses of lava. Okay, this would be very low viscosity lava that just ran out and spread out. Now, is lava currently flowing on the moon? Certainly not, but it flowed a long time ago, creating the maria, the large, dark, flat areas. Okay, the moon has many craters. They're from meteorite impacts. Okay, so we see lots and lots of evidence of meteorite impacts. The moon is covered in them. We can see whole sections of them. We can zoom in on the maria and even see craters on top of them. Okay. The far side of the moon has some craters, okay? Well, quite a few, right? So the cratering is pretty extensive on the far side of the moon, but no maria, okay? So those dark patches, the evidence of previous lava flows, only exist on the side of the moon that faces Earth, okay? And when we talk about far side of the moon and near side of the moon, we're talking about the visible side and the invisible side. Both sides have day and night cycles, okay? Because the moon does rotate on its own axis, but the moon is in, well, I'll come back to this idea in just a moment, but I'll say it now. The moon is in orbital resonance. Okay, important term for this chapter because it applies to both Mercury and the moon. Okay, more partially to Mercury, but very well to the moon. And that means that only one side of the moon is ever visible to Earth, because only the moon always presents one side to Earth, because it has an exactly matched orbital period around Earth and a orbital or a rotational rate around its own axis. Those two values are synced up, okay? All right, so what about Mercury? Well, Mercury cannot be imaged well from Earth. The best pictures have been taken by space probes that have passed by it. So we see an example. It looks a lot like the moon, right? It's kind of just plain dusty material, fairly reflective, lots of cratering, okay? Cratering on Mercury is indeed similar to that on the moon, although the craters are less densely packed, so there's definitely less cratering, and 40% of the surface is covered by intercrater plains, okay? So fewer craters. Okay, so here it is. Here's that idea of orbital resonance. Now, orbital resonance sometimes goes by another name, okay? Because we're talking about rotation here. It's called tidal locking, and that's a good name for it for a couple reasons. First of all, because it has the word lock in it, and that makes it clear that one side is locked to us, right? So we only see one side of the moon. There's this locking effect. The tidal effect actually has to do with how this process happens, okay? So what it means is that the moon's rotation rate is the same as the time it takes to make one revolution. So the same side of the moon always faces us. And again, the tidal part comes from the fact that process of the moon always having one side face us is because the moon has slowed down in its orbit due to pulling on Earth's oceans, which create the tides, hence the word tidal. But that energy it takes to pull on Earth's oceans takes away energy from the orbit, making it eventually get in the state that we see today. So the moon wasn't always tidally locked. It has been for billions of years, but in the very beginning of its history, it was not. It took an energy process for it to become tidally locked. Okay, and that was due to pulling on the oceans and the work and energy it took to move all that liquid water. Okay, all right. So Mercury was long thought to be tidally locked to the sun. Okay, so it was kind of the same idea. It was very close to the sun. Obviously, there's no oceans on the sun, nor are there oceans on Mercury, but the sun has fluid properties, so Mercury can tug on the surface of the sun, and the plasma that the sun is made of serves that same purpose of being a fluid, and it taking the energy required to move that plasma from the gravitational pull of Mercury. Now, obviously, Mercury isn't pulling the sun around, but it is pulling small amounts of the surface plasma on the sun. Okay, but it turns out that it's not tidally locked. Okay, 1965, we found out that's not true. But there's something else. Rather, Mercury's day and year are in a 3-2 resonance. Okay, so this is very interesting. Mercury rotates 3 times while going around the sun twice. You see that? So, in other words, its day is 2/3 as long as its year. Okay, now the moon, its day effectively, now it's weird to call it a day because it doesn't orbit the sun, but the time it takes the moon to rotate on its own axis is exactly the same as the time it takes to orbit Earth. Not so for Mercury, it's 3/2. Okay, so it's about 60 Earth days for one Mercury day, okay? Which means if that's 2/3 as long as the year, that means it's about 90 Earth days for a Mercury year. So you see, like, unlike us, where a year is 365 times longer than our day on Earth, Mercury, no, it's only 1/3 again as long, right? So not nearly, or half again as long, right? Because it's 60 to 90, not nearly as dramatic, right? So they have Mercury has depending how you think about it, it has a really short year or a very long day. It's more like it has a very long day, right? Okay, this is a wonderful picture here, this one here, this diagram, showing you the idea of what it looks like to be on a particular side of Mercury, right? So if you were standing right here, like the stick figure we saw for the moon, if you were standing here on this side where the arrow is, then this would be high noon, right? Because you'd be looking at the sun. And then, like all the planets, except for Venus, Mercury orbits in a counterclockwise rotation as seen from above the ecliptic plane. So as we go through that counterclockwise rotation, we can see the different directions that person would face, right? So they would see the sun start to set, okay, right? So then they'd see the sun set on the 44th day, and then they'd come around, and then the sun would continue not to rise, okay? So we can see when we get to, let me go back, when we get back to day 88, because we have day 74 here, and we go to the next diagram, day 74 takes us over to day 88, and look, the sun still hasn't risen. Look, there's a very long night. The sun doesn't rise until day 147. So you see that the day sets, or the sun sets, right, at day 44, okay, and then it doesn't rise again until day 147. And so there's this very fascinating asymmetry about how the sun moves through the sky from an observer on Mercury's surface, okay? And it all has to do with this 3-2 resonance. Okay, so let's talk a little bit about air sticking around, okay? So this is one of the kind of quantitative topics we can cover in the chapter, and that's the idea of the escape velocity, which we talked about briefly, right? Because I was talking about, sending rockets from the moon and Mercury, that escape velocity, but it doesn't just apply to rockets, it also applies to molecules. So if the escape velocity of molecules is lower than their average random velocity, because molecules bounce around all the time, right? Just under normal temperature effects, then you know what happens to those molecules? They leave the planet never to return. And a planet like that, or a world like that, in the case of the moon, can't hold on to an atmosphere, okay? So air molecules have high speeds due to thermal motion, okay? Even in at room temperature, you have molecules moving around at 200 meters per second. You don't notice it because they're tiny, right? But they are moving at very high speeds, okay? So if the average molecular speed is well below the escape velocity, few molecules will escape, okay? So that's the case of Earth, all right? So that's also why we don't have much hydrogen in our atmosphere, because the average thermal velocity of hydrogen isn't that much less than the escape velocity of hydrogen. So there's a chance the hydrogen molecules will escape. So over time they do. So our atmosphere is primarily composed of larger molecules like nitrogen. They're more massive, so they have lower thermal speeds, okay? Which means they're less likely to escape, and we have them, they've stuck around for hundreds of millions of years, and we have an atmosphere with lots of nitrogen in it, and obviously as well as oxygen, okay? Okay, now, the thing is, that's not the case for the moon or Mercury, okay? So the moon and Mercury can't hold on to nitrogen or oxygen because even though they're more massive, they're able to escape because those smaller worlds have those lower escape velocities, okay? So higher temperatures, right? That's also an issue. So Mercury has a much higher temperature because it's going to be close to the sun. Now it has really cold temperatures too at night, but its daytime temperatures are incredibly hot. Okay, so during the day those molecules could escape. Okay, and then the smaller planets, just the fact there's less gravitational pull exacerbates that effect of losing molecules. So there's just really no chance for these worlds to hold on to their atoms. Mercury, especially because of its hot days and its relatively small size. The moon, mostly because it's relatively small size, and you saw its very low escape velocity. So these two planets, or one planet and one moon, can't hold on to atmospheres. Okay, so here's the idea, like kind of the probability curve, okay? Because the average molecular speed is not like all the molecules move at the same speed, but they have an average based on this probability. So this is the number of atoms that are moving at a certain speed. This is just the speed, okay? This would be in probably kilometers per second based on this scale, okay? And so, there's this certain likelihood, right, that if you have 99% of the molecules that are on a certain side, then over time those molecules are going to escape. Okay, all right. So they have a range of speeds, but they're over time they will escape if there's a certain probability that some of them will. Okay. All right. So back to our main topics with one other little side topic, which is lunar exploration. So the Soviets had the first contact with the moon. Okay, first to land a spacecraft there. So first spacecraft to fly past the moon, rather, not to actually land on it, but first to fly past it, January 1959. Soviets obviously were first in space too with Sputnik. All right, the first spacecraft to crash land on the moon, September 1959. First pictures of the far side of the moon, October 1959. So they're all a bunch of firsts. So the United States, however, eventually got a first, and they were the first to land a person on the moon in July 1969. Okay. All right. So lunar cratering and surface composition. Okay, so we talked about how there's lots of craters on the moon. Well, meteoroids strike the moon, ejecting material. Explosions eject more material, leaving a crater. Okay, so the meteorite crashes in, throws matter apart. It releases a lot of energy. That energy basically, because it's so hot that a lot of the rock is essentially vaporized when it crashes into the surface, and that leads a crater. That's also why most craters are round, even if the angle comes in is not straight on, because the energy gets released spherically. Okay, because you have the energy from the explosion coming out. Okay. So craters are typically about 10 times as wide as the meteoroid creating them, and twice as deep. It's a good kind of general rule. The rock is pulverized to a much greater depth, and most lunar craters date to at least 3.9 billion years ago. Much less bombardment since then. So this is so interesting. And we talked about this a bit when we talked about the history of the solar system and the formation of the solar system, that era of bombardment. So you look at the moon, you say, oh, it's always getting hit by meteorites, and you might think, or meteoroids, and you might think, oh, well, that's a continuing process. And yeah, there are still some meteoroids that are crashing into the moon, but the vast majority happened billions of years ago. And those craters are mostly that old, okay? There's just not as much stray material out there as there was early in the solar system, okay? Craters come in all sizes, right? There are tiny, tiny little craters that are from, just like pea-sized meteorites, and then there are very, very large ones as well, okay? Yep, tiny, microscopic in size, okay? So the moon, the term that often comes up with the moon is the regolith, and this is the layer of dust left over by meteorite impacts. Because really, there's no soil, obviously, right? And there's not a lot of pure rock. There are the lunar maria where you think, okay, well, those are big lava flows. That might be pure rock. But even that has been largely covered over in this dust by the previous impacts, okay? And the moon is still being bombarded, but mostly by these micrometeoroids, tiny, tiny ones. Okay, and those we often will point out that these footprints that were left by astronauts on the moon, they will be eventually erased by millions of little collisions with micrometeoroids, because there's no atmosphere for them to burn up, because these types of micrometeoroids would just burn up in an atmosphere like Earth's, but there is no atmosphere on the moon, so they don't. They will crash into the regolith, and they'll crash into the footprints. But obviously, it'll take lots of such collisions to actually erase the footprints, because there's no wind on the moon. And so over hundreds of millions of years, then the footprints would eventually get erased by individual little collisions of tiny meteoroids. Okay? And it's important to note that meteorites also hit Earth. Okay? This crater is in Arizona, right? So there are huge examples of large impacts here on our planet. Okay? And more than 3 billion years ago, the moon was volcanically active. So this is getting back to the Maria. Okay? And the ryle here was formed then. Okay? The ryle being this particular geographic or geological formation that we're looking at here in this image. Okay? And so, is it still volcanically active? No. But early on, the moon was. And so when particularly large meteorites, like the one that hit Earth in Arizona, crashed into the surface of the moon, it broke through the crust, allowing that lava to flow out, creating those lava plains. Okay? Okay. So, back to Mercury. Mercury is less heavily cratered than the moon. Some distinctive features are the scarps. Okay, now scarp is just the word we use for cliffs on Mercury. So kind of a Mercury, it can be applied anywhere, but you don't hear the word come up very much. When we talk about scarps, we're talking about cliffs on Mercury. They're incredibly long, so these very extended cliffs that are hundreds of kilometers long. All right, and they can be as high as three kilometers high. Right, so these are dramatic cliffs. Right, maybe you don't see it from the space images, but this is an example of one of these long cliffs running along the surface. Okay. Now, we think the scarps are left over from Mercury cooling and shrinking, all right? And as the planet shrunk, it actually ended up with creases on its surface. So the cliffs are an effect of that. The cliffs don't come from plate tectonics like on Earth, right? Not this idea of, like a dynamic crust moving around and a liquid core that's been liquid for billions of years. Instead, it was just a cooling process that left a single effect, being the cliffs, okay? There is the Caloris Basin on Mercury. It is a very large impact. Okay, it's on the opposite side of the planet. All right, from the weird terrain. All right, so it's just a huge, huge impact. The weird terrain is thought to result from the focusing of the seismic wave, right? So we have an example of an impact, the Caloris impact, that was so powerful that it sent a significant amount of energy all the way through the planet and actually caused mountaining. So, it's kind of like, a mountain to form on the opposite side. So we have a planet that was essentially ringing because it was hit so hard, okay? So the moon's density is relatively low. I pointed that out. It has a standout low density for being a terrestrial world. Okay, world being a catch-all for planets and moons. Okay, and it has no magnetic field at all. Okay, we definitely talked in the last lecture, in lecture 7, chapter 7, about how the Earth has a distinctive magnetic field. Okay, so magnetic fields are important for talking about whether planets have them or not. Okay, the moon definitely does not have a magnetic field. Okay, it cannot have, which means it cannot have a sizable iron or nickel core. Okay, so we don't think it really has a metal core because its low density and its lack of magnetic field suggests that there's just very little metal in the moon. Okay, so it has a very thick crust. All right, it's mostly crust. Mercury, on the other hand, is much denser than the moon, okay, and does actually have a weak magnetic field. The field is due to a molten core, all right, so there's probably a small amount that is still molten, so it's not completely geologically dead, but that energy really isn't coming up to the surface. There's no active volcanism on Mercury that anyone has ever discovered. So the idea that, here's Mercury, right? So its core it's just got a little bit of energy, probably from radioactivity, a little bit of cooling left over, okay? All right. But what's interesting is that Mercury does rotate so slowly that we not really expect a magnetic field. So the magnetic field is a little confusing to scientists, and it might just have to do with maybe some particular elements that are able to create a better current than we would theorize, because most models, based on how much cooling Mercury has done, suggest that Mercury shouldn't have a magnetic field at all, but it does. So it's kind of a fun thing to think about, that Mercury has a magnetic field, even though it might not, maybe it shouldn't have one based on our understanding of magnetic fields, which means we just need to understand magnetic fields better. Okay, but one thing that is worth considering is this idea that we expect Mercury to be very cool or much cooler in its core, and that's due to its smaller size, because smaller things cool faster. There's a idea that's universal to science called the surface area to volume ratio. All right, so surface area to volume, okay? And the idea is that the surface area grows as the square of the radius, and the volume grows as the cube of the radius. So that ratio doesn't remain constant. As you get bigger and bigger, you have less surface area to volume. You can fit more inside, which means big things cool slower, not just because they're bigger, but because they literally have more interior per surface area. Okay? So that's a big deal for planets, as well as, like, I guess, cooling things that you bake in your oven, because it really has a dramatic effect over billions of years on whether we expect planets to be completely cooled off or to have leftover heat like our own world. Okay? So the current theory of the moon's origin. Well, we think it came from Earth. It was part of Earth and it broke off from Earth. The theory suggests that a glancing impact of a Mars-sized body, like a planetoid, like an early planetoid that might not be left, maybe fell into Jupiter, or became part of the asteroid belt, but early in the primordial solar system, where there are different planetoids, well, one of them hit Earth. Earth at this point being maybe mostly formed in its current orbit, and Earth was in a completely liquid, molten stage at that point. And that glancing impact, kind of shown over here, broke off a huge amount of that liquid molten matter, throwing it hundreds of thousands of kilometers off into space. A lot of that gravitationally would have just fallen back onto Earth, but some of it would not have. Some of it would have started gravitationally pulling itself together and eventually formed a clump. That's the moon. Okay? So that the ejected matter that didn't just fall right back to Earth, eventually formed the moon. And the Earth obviously then took hundreds of millions of years to cool back down and start to have its own crust form. But in the meantime, the moon was formed. And one thing that really contributes to the validity of this model, other than that we can model it with computers and say, oh, look, it works, is that it explains why the density is so low. Because it explains that the moon was not formed independently from the accumulation of matter in the primordial solar system, but instead was broken off, composed almost entirely of that lighter matter that was on the surface of Earth. Because the Earth was fully liquid, which means all the denser stuff would have been in the core. And the glancing impact didn't disturb much of the denser material. It only knocked off all the less dense material on the surface of the early liquid Earth. Okay? So we got a good explanation of the low density of the moon. It explains its large size. It's a model that makes a lot of sense, a theory that makes a lot of sense. Okay? So in terms of the time, right, we think that 4.6 billion years ago, that was when the formation of the moon happened. Okay? And then that was followed by heavy bombardment that liquefied the surface. At about 3.9 million years ago, bombardment was much less intense. It already started to, in this time frame, in that 500 million years, bombardment slowed down. Just again, a testament to how long ago the early bombardment happened. All right, and then 3.2 billion years ago, volcanic activity stopped. So even the Maria that we see, the dark material we see on the side of the moon that faces Earth, that really kind of stopped forming 3.2 billion years ago. And ever since then, the moon has been mostly in the state that it looks at. If you were to go back 3 billion years ago and look at the moon, it'll look a lot like it is today. Okay. All right. So we know a lot about the moon. It's close to home. We've been able to study extensively. We're not able to study Mercury as much, so we have a lot of unanswered questions, right? It's much less well understood. Okay. We do know it was formed about 4.6 billion years ago, around the same time as Earth. We know that it melted due to bombardment and then cooled slowly, and we know that it shrank. At least that's what all the cliff structures suggest, and that's why we see that crumpling, such as those long cliffs, the scarps. Okay. All right. So let's summarize everything here. So the main surface features on the moon are the Maria and the highlands. Okay. They're both heavily cratered. Both have no atmosphere. All right. That is both being Mercury and the moon. and large day-night temperature excursions. Okay, so very hot days, very cold nights, because that's the thing about having no atmosphere. There's no regulation of that. It's, you know, when the radiation of the sun is hitting the surface, things heat up fast, and as soon as the sun sets, things cool dramatically, right, by hundreds of degrees. Okay. Tidal interactions are responsible for the synchronicity of the moon's orbit and the resonance of Mercury's. Okay. Moon's surface has both rocky and dusty materials. There's evidence for volcanic activity, the maria. Mercury has no maria, but does have extensive intercrater plains and scarps. Okay, all right, well, thank you so much for watching this video about the moon and Mercury. I hope it has been interesting and informative.